In 1946, Imperial Oil, a Canadian petroleum company, reluctantly decided to undertake a final attempt at finding oil in Alberta. After drilling 133 consecutive dry wells and not having made any major oil discoveries for 25 years, the drilling crew had low expectations. However, they were soon proven wrong. A year later, Leduc No. 1 drilled into layers of wet gas and porous rock laced with oil, and quickly started producing up to 1,000 barrels a day. This discovery remains an important event in Alberta's history, marking the beginning of a 20-year period of intense exploration, discoveries, and expansion of Alberta's oil industry. Today, fossil fuels are key components of Alberta's economy. Last year, Alberta generated $71.5 billion with its energy sector alone. In 2017, 6.1% of employment in Alberta was related to mining, oil, and gas extraction, with about 140,000 people relying on this industry for work. For now, let's take a break from all the cinematics and let's delve into the subject.
Although there are many ways to extract natural resources from the environment, they are divided into two main types: conventional and unconventional. Here we see a cross-section of the Earth. Conventional resources are found in reservoirs constrained by impermeable zones. These fields have high recovery factors and are easily harvested. Once drilled into, conventional wells remain productive until the reservoir is depleted. Unconventional resources, however, are distributed continuously through rock formations at depth. Because of this, they are also called continuous resources. Since the rock formations are impermeable, these resources have lower recovery factors and require additional technologies to extract. This is where fracking comes in.
But what the frack is fracking?
Hold up. Let me draw it out for you.
First, a well is drilled into the layers of the Earth's sediment. This well is usually encased by cement and steel to prevent leakage. The well is drilled until it reaches a layer of permeable shale rock by a vertical pole called a wellbore. Once it is about 2,500 to 3,000 meters deep, it rotates 90 degrees to drill through the shale rock horizontally for about 1.5 kilometers. A perforating gun is then fired through the well's exterior into the rock, creating many small holes. Months after the initial drilling, a high-pressure water mixture is pumped through the well, which causes fractures in the shale rock. Compartmentalized gas and oil is then released, and the fluid is collected for further treatment.
Oh, I get it. Anyways, carry on.
Given that oil and gas are non-renewable, easily accessible conventional resources are becoming harder to find. Because of this, and as shown in this data and these projections by the Canada Energy Regulator, production of conventional oil in Alberta has been decreasing, dropping from about 750 million barrels per day to around 300 since the year 2000. Meanwhile, unconventional production is projected to increase steadily. With this, Alberta is expected to become more reliant on fracking technology.
By stimulating fluid from impermeable shale rocks that were previously considered unviable energy sources, hydraulic fracturing has significantly improved the production of natural gas. Given that its combustion emits 30 to 40% less CO2, 80% less nitrogen oxides, and almost 100% less sulfur dioxide, particulates, and mercury than the burning of coal. Natural gas is seen as a favorable alternative until more sustainable energy sources become viable. In fact, natural gas is the cleanest burning of all fossil fuels by far. Unfortunately, natural gas does have its downsides. Since natural gas is primarily composed of methane, its extraction may considerably increase the emissions of this greenhouse gas. In fact, methane emissions occur throughout natural gas production, occurring during well completions, venting, transport, distribution, leaks, and even storage. According to Howard et al., up to 7.9% of all the shale gas being produced could be lost through these emissions. While methane has a shorter atmospheric lifetime than CO2, its radioactive forcing is 120 times greater. In short, this means that although lowering CO2 emissions is necessary for long-term climate change mitigation, the increase of methane emissions could potentially expedite climate system tipping points in the short term.
A concern more specific to hydraulic fracturing is its immense requirement of water. According to Entrican et al., wells often use around 7.5 to 26 million liters of water. Since saltwater inhibits the production of gas and oil by significantly increasing corrosion and scale deposition rates within the rock formations and equipment, freshwater is preferentially used. This means that millions of liters of water must either be produced from water sources in the area or taken from local reservoirs and brought by trucks. Because of this, concentration of fracturing efforts in small areas may negatively affect their natural streams. This figure from a study done by Entrican et al. Demonstrates exactly this. As we can see, the turbidity of water streams increased with an area's well density. Since less water was available for dilution in these high well density areas, contaminants and organic matter became more concentrated and ultimately lowered the water's quality. Not only can hydraulic fracturing affect the quality of natural surface streams, leaks and upward migration of fluids from shale gas reservoirs may also affect subsurface waters.
Hold up, didn't the documentary say that shale reservoirs were like super duper deep? How can fluids migrate that far?
I guess I can do a few more drawings. I remember some stuff from a publication by the Lawrence Berkeley National Laboratory.
For example, negligence or improper practice when building the cement and steel cylinder coupled with the high pressures of the process may result in damage to a well's integrity and cause leaking of the fracking fluids. The most probable of these mechanisms occurs when other producing zones located above the target zone are drilled through. If the well cement exterior is improperly constructed, oil and gas from layers of sediment above the target zone enter its gaps. Due to the high pressures of this process, the oil and gas migrates upwards. This has a significant impact on subsurface waters and contaminates drinking water.
While upward migration and well leaks may be avoided with careful planning, the contamination of water during hydraulic fracturing remains unavoidable. To attain a viscosity that encourages fracturing and gas flow, as well as discourages microbial growth and corrosion, additives are added to water to produce a fracking fluid. While the composition of these fracturing fluids may vary greatly, they typically include additives such as friction reducers, surfactants, biocides, pH adjusters, and scale inhibitors. While some of these are harmless, others have been shown to be highly toxic or
This freshwater
carcinogenic.
contamination is worsened during the fracking process. As oil and gas are pumped to the surface, deep groundwaters containing elevated levels of metals, dissolved solids, organics, and radionuclides are brought with it. The result? Millions of liters of highly contaminated water. Disposal of these waters poses a major challenge for oil and gas producers. In some situations, these waters are transported to local wastewater facilities. However, recovered hydrofracking waste often contains dissolved solids concentrations that exceed these facilities' capabilities. And while industrial wastewater treatment plants are better equipped, using processes such as reverse osmosis, filtration, and chemical precipitation is extremely costly, having estimated costs of over $5 per barrel.
An alternative to treating toxic flowback is to inject it underground. Considering that well injections have estimated costs ranging from only 50 cents to $1.75 per barrel, this is a much cheaper alternative. Unfortunately, this disposal method has an important drawback. The injection of waste into deep geological strata works to increase the amount of stress within the Earth's crust. From this, forces holding faults in place may be brought out of equilibrium. Without this equilibrium, the faults slip and send shockwaves towards the surface. This may well be what happened on March 4, 2019 near Sylvan Lake. Just before 6 a.m., a 4.6 magnitude earthquake rocked the area, leaving about 4,600 people without power. While no immediate damage was reported in Sylvan Lake nor Red Deer, earthquakes of this magnitude have the potential of breaking dishes and windows. Soon after the incident, the Alberta Energy Regulator confirmed that Vesta Energy had undergoing fracking operations in the area. Between March and May, the company was ordered to suspend all its activities to protect both the public and the environment. All in all, the issues presented by hydraulic fracturing highlight Alberta's need to reduce its dependency on fossil fuels. While the extraction of conventional resources has allowed Alberta to prosper in the past, these resources are becoming increasingly sparse. Even though a shift towards unconventional production of oil and an expansion of its natural gas sector may help sustain the province's economy, it would also increase the province's methane emissions, its use and contamination of freshwater, and seismic activity.